We're going to get this show on the road. I'm Sean Marcotte, and this is Steve Myers, and we are Harmony's co-advisors. As I said on Saturday, for those of you who are there, it takes 2 geoscientists to equal 1 atmospheric scientist, apparently. So today, it's with great pleasure that I get to introduce Harmony, that Steve and I get to introduce Harmony for her Ph.D. defense. Harmony started her path a little differently than most students, I think. Well, differently in the sense of how many directions and shifts she's taken. She came here in 2013 from Nanjing University.
Nanjing University of Information Science
Yes.
and Technology.
Newest, yeah. In 2013, and then started her PhD with Zhenghun Liu, and then when Liu left to go to Ohio State, Steve and I became her co-advisors to see her through the remainder of her PhD. Her topics that she's going to talk about today bridge this gap between atmospheric sciences and geosciences, with the melding really being statistics. And what she's doing and what she's done as part of her PhD is she's applied statistical techniques to ask questions about paleoclimate problems. So these are problems associated with geologic questions that Steve and I and others in the geology community have had for a long time, which have widely gone unappreciated, simply, in my mind, because there are very few people that can actually do the work. And the reason they can't do the work is either they know what the questions are and they're trained as geologists and they have a full grasp of what the problems are and all the uncertainties and everything else, but they don't have the statistical firepower to actually answer the questions the way that you would want to see them answered. And this is where Harmony comes in, where essentially Steve and I have been working with her not to train her as an atmospheric scientist, but to train her as a geologist, so that she can then apply these tools to these larger scale questions that have largely gone unanswered in the geosciences. And she's been quite successful at it, and it's been a real pleasure co-advising her with Steve. And I'm really excited that we've gotten to this point already. And I'll let Steve say a few words.
I would just like to tell you why I was so excited, and I have been so excited to see the development of Harmony's work. So our planet is going into a new realm, right? Temperatures are rising. The temperatures we're observing today are higher than anything from an instrumental record. The amount of CO2 in the atmosphere is higher than anything we've seen in an instrumental record. The way we can come to understand where we're going is to use climate models, which is something Harmony has done, but also to interrogate and look at the geological record. There are some fundamental problems, some elephants in the room that my community has been sort of pushing to the side, that inhibit us from fully leveraging that data, the geological archive, to talk about our future. It ultimately comes down to resolution, because what unfolds over the next century and millennia is mixed in the geological record. So imagine this as a data logger where the time is changing, the rate of your data logging is changing, and not only that, it's being mixed by some sort of noise source. And your goal is to retrieve the real signal from that. So this is what Harmony has been able to achieve in her dissertation. And again, it's been something that the community has largely ignored because they didn't know how to really solve it in a lot of ways. The basics were down, but really having the skill, the comprehensive knowledge from the mathematics, the statistical, the geoscience, and even climate modeling, it's very rare. So this is where Harmony has excelled. And she will now tell us about this. And let me tell you that what she has achieved is one of the ambitions of my NSF Career Award, which ends this year. And I was always hoping that it might be possible to do this, and Harmony's done it. So take it away, Harmony.
Thanks, Sean and Steve, for the awesome introduction. So today I'm going to talk about bridging the model data gap in paleoclimatology, data assimilation, and waste removal from marine proxies. Climate of the past can be estimated by proxy-based reconstructions, for example, tree ring data and ice core data, and some chemical analysis from the ocean sediment data. These proxy reconstructions have sparse network, irregular temporal sampling, as you can imagine, and all of them are indirect measurements of the climate state variables. Therefore, they usually have high noise and potentially biased. The past climate can also be estimated through model simulations These are mathematical representations of the Earth system that have model physics that is consistent with our current understanding. And the output of the climate model simulations are spatially and temporally coherent. There's a third approach by merging proxy observations with the model simulations to get a data simulation product. This product will have model physics, and they will also be consistent with the proxy observations. And the most importantly, the output is temporally and spatially coherent. So it's like a reanalysis data set for the paleoclimatology community. So the third approach is very promising. So we have these three aspects of state estimation of the past climate: proxy-based reconstruction, model simulation, and paleoclimate data simulation. One chapter of my dissertation is going to focus from the observation perspective, which is how to reduce the marine proxy bias. This is going to be my chapter 3. And another chapter in my dissertation focuses on the third approach, which is paleoclimate data simulation. Specifically, try to solve for the optimum paleo data simulation method for state reconstruction in the past. This is my chapter 2. Sadly, I don't have anything in the second aspect. I would like to do more if I have more time. I have the third chapter, which is the last chapter, which is an application of data simulation methods for modern day applications, which is kind of independent from this grand picture. So today I'm not going to talk this chapter. So here's my 3 chapters. Chapter 1, assimilating atmosphere reanalysis in coupled data simulation. I'm not going to talk about this one. I'm going to spend 2 slides talking about the paleoclimate data simulation perspective. It's a systematic comparison of particle filter and ensemble common filter in assimilating time averaged observations. The major of the talk today is going to focus the 3rd chapter, which is from the proxy observation perspective. I'm mixing the deep sea sediment records, a study on the observation effects through convolution and deconvolution. So chapter 2, a systematic comparison of particle filter and ensemble common filter in assimilating time averaged observations. So these 2 filters are most popularly used methods for paleoclimate state reconstruction in the literature. Some of you might know, for ensemble common filter, it is a Monte Carlo application of the original common filter. We have an ensemble model forecast, and we merge the observation with the model forecast to get analysis state. And this analysis state will be used as initial condition for the next analysis cycle. And many of you probably know that ensemble common filter have a very fundamental assumption, which is they assume the probability distribution of the climate state has to be Gaussian. Because of this assumption, we can derive this very linear update equation by solving for the maximum likelihood. And we get a linear combination of model forecast and observation XO to solve for analysis state. And the weighting between them is proportional to their relative error. So larger error will have a smaller weight, and smaller error will have a larger weight. For particle filter, it's kind of different from ensemble common filter. It also requires ensemble implementation, but it doesn't require a Gaussian assumption. So in some sense, it allows non-Gaussian characteristics to emerge. And the analysis state of particle filter is solved as weighted sum across the ensemble members. So this is the illustrative figure showing different ensembles. You forward the model in time and arrive the analysis state to get an observation, and then you merge the observational information into the simulation by assigning each model simulation a weight, calculated as how close they are to the observation at this time step. Some of the simulation can be very bad, they're far from the observation, and we might remove them. They will be assigned as a 0 weight. And some of them are very close to the observation, will get very big weight. And then we have to resample. We have to remove some simulations and duplicate some of the good simulations to maintain the same ensemble size and continue the model simulation. So the reason to compare them is there's lots of papers on particle filter, but particle filter is also famous for being stupid because it requires a huge sum of ensembles to fully capture the state. And we all know our current Earth system have very high dimension, which is really challenging to run particle filter. So we implement these two filters in the fully coupled GCM foam and perform some pseudo proxy test, simulating seasonal pseudo observations. The experiment ran for 200 years using 16 ensembles for ensemble common filter and 48 ensemble for particle filter, and we performed some sensitivity test on some parameters. The results we find is that ensemble common filter is better than particle filter in almost every single way, despite particle filter has some theoretical superiority over ensemble common filter. So ensemble common filter is better in terms of hemispheric reconstruction, local reconstruction, the ability to constrain the mode of variability, and most importantly, computation power. We attribute the success of ensemble common filter to three main reasons. First, Gaussian assumption is somewhat sufficient in our application. Second, we use a really large localization scale, which is very different from meteorological applications. Because we have such a sparse observation network, we really have to utilize the large-scale covariability in the climate system, such as ENSO and PDO, such that we can use a very limited observation network to constrain the whole system. So now we're moving to the chapter 3, which is going to be the main part of this talk. We're going to mix the deep sea sediment records, studying belturbation effects through convolution and deconvolution. So we're going to go through what is belturbation and why do we care, and then how do we model it. The quick answer is we can use impulse response function to characterize this deterministic process. And we're going to go through how to remove its effects from an existing record. I'm going to go through the inverse modeling approach, talk about the methodology and sensitivity tests. And then we'll apply this method to a very important paleoclimatology data set, LR04, to check the question, does belturbation actually affect climate state estimation from the past? We are going to focus on specific geological time period, marine isotope state 5e, and look at the sea level reconstruction. So what is belturbation? Most of the paleoclimatology proxy reconstructions rely on the preserved organic biomarkers, and many of them utilize the fossilized hard parts of the marine organisms, such as foraminifera and coccolithophore. And these are marine organisms that have only one cell and live in large quantities in almost every part of the ocean. And the water environment they grow up in will have the fingerprint from the climate state at that time. So by analyzing the chemical composition and isotopic composition in their shells, the fossil of their shells, we can get some hint of the past climate state variables. For example, the undersaturation in the alkanols in the shells of coccolithophore, we can get a relationship between temperature and the undersaturation ratio. And we can use the magnesium, calcium to infer temperature, and we can use benthic O18 to get a hint of the ice volume in the past, and also it's kind of a mixed information of the deep sea temperature and ice volumes. So when these marine organisms die, they fall into the seafloor and form the ocean sediment. The ocean sediment will accumulate at a speed about a few centimeters per thousand years to 100 centimeters per thousand years, which is very extreme. But before they are buried down deep into the core, they will be constantly mixed up and down by the marine living things who live on the seafloor or in the seawater sediment interface. Also, the water wave at the seafloor can also stir things up. So imagine if geologists drill an ocean sediment core here and perform chemical analysis on each layer, and then retrieve back a series of chemical compositions or isotopic values to reflect the time evolution. If there's mixing with net positive, the values you're looking at is actually mixed. So imagine you have a time series of climate signals look like this. It's deposited into the ocean seafloor, deposited into the sediment. As it passing through the mixing layer is the where the mixing can still reach the because below the mixing layer there might not be biological activity, so the signal will stay put. When they're passing through the mixing layer, the signal will be attenuated by the mixing, and also the phase might be shaped when they're passing through passing through this layer. Another way of thinking about it is thinking about of an instantaneous geological deposition, volcano eruption. It will deposit a layer of volcano ash in the ocean on the sediment. If you don't have mixing at all, and if you take a look at the concentration profile against the depth, you will expect to see a horizontal line here if there's no mixing. But if you have mixing, the particles in the ash particles will be diffused both upwards and downwards. You might get something look like this. And if you have a very strong mixing, imagine you enter into the mixing layer and got mixed evenly, instantaneously, you might end up with exponential decay curve. So these three different shapes characterize three different perturbation environments. One important feature I want to point out is that the recorded event peak here is always below the depth of original event. So in geology, we look at depth. It's like our time. So deeper depth means older time. So the peak below the original depth means that the event we're actually look at is not that old. It doesn't happen that early because it's perturbed. So you will have this recorded peak instead of it should be here if there's no mixing. So this is an important feature of perturbation. So from this figure, I just want to introduce the concept of impulse response function. It's a mathematical terminology for a response function like this. It pretty much characterizes a time invariant system. How will it modify impulse input? Once we have impulse response function, the next question is, how do we get the shape of it? What does it look like? One way of finding an impulse response function is by just looking at the instantaneous geological deposit, like a volcano eruption, and you can dig ocean core in different area and see how the volcano ash concentration looks like. So these profiles are from different cores in North Atlantic. So they will, because they're from different places, you will expect them to have different shapes. This is a very good characterization of the mixing condition that happened after the deposition of the volcano ash. Some other people use some empirical profiles like this, look like the exponential decay, based on some observations from geology. There's a third approach, which is use mathematical modeling. This is also the approach we're going to use in the later on slides. It's a very important perturbation model from Ignacio and Schenck, 1975. It's an advection diffusion model. If you look at this equation, actually it's pretty simple. It is just a one-dimensional heat advection diffusion model. We here use diffusion to model perturbation. So perturbation in this case is eddy diffusion. And the diffusion coefficient here we'll call it Bell diffusion because it represents how intense the perturbation is. And we use the advection term to model the sediment accumulation rate. So imagine your sediment is accumulating really fast. So anything that enters into the ocean seafloor will exit the mixing layer very quickly. So it will be less mixed, and vice versa. We have these, and then we have some boundary conditions that's designed for this application. Once we scale the equation to get the simpler version, which is dimensionless, the equation will be left with only one parameter g, which is a ratio between diffusion coefficient and the mixing layer depth and the sedimentation rate. These three parameters are the major, are characterize how intense the perturbation is. If if you have a very deep mixing layer, which means any particles that enter into a mixed layer will spend there for a long time if the sedimentation rate is not very big. And sedimentation rate can also determine how long you will stay in this mixing layer. And the diffusion is simply the diffusion coefficient. After solving this equation, we get a complicated looking analytical solution. It looks very complicated, but the impulse response function itself looks very simple. So this equation will give you what the response function look like at any depth and at any time. The shape of this function is determined by g parameter. It's here. So I call this g parameter shape parameter. I'll show you how it looks like. I'm going to show you two cases. One is g equals 3, rapid big, and one is g's have a small value represents a weaker perturbation. And these are depth. So here is C4 and going down, going deeper down 4. And this is a mixing layer. After this curve, they will exit the mixing layer. I'm also going to show when the original depth of deposition. So here is when something is deposited into this. The red curve shows where the original deposition layer is. So the recorded event peak is always below the original depth of deposition. So for this case, for smaller perturbation intensity, the response function is more symmetric, but the recorded event peak is still below the original depth of deposition. Okay, so this is just a figural version of the previous video, just showing the time evolution of a bunch of impulse response functions. So we can focus on this plot. A plot here is g ranges from 0.02 to g equals 30, and then we give a very extreme value, g equals 100. G equals 100 is this dark blue curve. It have a very pointy top. This is approximately the exponential decay curve. Also, you can notice when g equals 3, which is a light blue curve, after when g is further increased, this shape is not changed that much. This is the one characteristic of this model. So if g is become bigger than 10 or something, people will say that the shape function is indistinguishable. When g decreases, you can see the mixing function become more and more symmetric. And when g equals 0.02, you get this very symmetric looking curve. And you can imagine if g approaches 0, this will thin into a vertical line, just like the volcano eruption. To give you a sense what it means, so if we take the g equals 3 case, this green curve here, for example, if we have a global average mixing layer 10 centimeters and a 1 centimeter per kDr sedimentation rate, with g equals 3, we can get biodiffusion about 30 centimeters squared per kDr. That's how you calculate the d given some of the parameters.
Sorry, in order to get the one-sided exponential decay with just a cliff, do you have to specify zero diffusion below 4 depth units? Or is there a little soft top to that, and it's actually a slope?
You mean here?
Yeah. Why does that diffuse downward?
So this model, if you solve it mathematically, when g is very big, it is reduced to a simple exponential decay model. It's equivalent. So it looks it approaches that solution, but it's not exactly
Not quite.
the same.
It's rounded and there's a little bit of a
Yeah,
slope.
it's probably, if you zoom in, there's probably still a little bit one part, but it's very indistinguishable. That model is more simple. It's the first, that's earlier than this model, when people use the instantaneous mixing. So, we're going to go through 2 sections. One is forward modeling, where if you have an input climate signal, and you know what the perturbation environment is, you can use a forward modeling approach to calculate what the output look like. This is good for quantification of any perturbation effects given a known input signal. But this is the tricky part, because in the real world, you never know what the input signal is. And there's another inverse modeling approach, which is more for real-world application. is given a proxy observation, which is actually a bell-curve signal. It's like an output from here. So given a bell-curve record, and you can estimate what the bell-turbation has gone through, and then we can back out what the input is. This input is just like a regional input climate signal, or it's like the truth for data simulation people. Like the truth you're always trying to estimate, but you never know what it actually is. So for forward modeling, it's relatively straightforward. So putting a time series, putting an input time series fx into a system characterized by an impulse response function, we can get the output time series by simply calculating convolution. So it's fx convolved gx and get the output hx. One thing I want to point out is that think about how you get one point here at time z or at depth z or time t. It is a weighted sum of the points in the input signal. The weighting comes from the IRF of the impulse response function. You calculate the weighted sum of these black dots to get these red dots. Think about the physical meaning in this convolution. So this is a depth it is deposited, and this is a deeper depth, and this is a shallower depth. Deeper depth means past, shallower depth means future. So to calculate the value at current point, you need information from both past and future. So which makes our application is actually non-causal. I want to point out this is later when we're doing inverse modeling. We need to use some commonly used methodology in signal processing, but in signal processing, what they usually are handling is causal filter, but we are non-causal filter. That's the stuff we have to deal with when we're doing our application. Because bell-turbation makes things both upward and downward. That's why it's non-causal. So here, I'm going to show you a forward modeling of an artificial time series and show you what bell-turbation can do to our climate signal deposited into the seafloor. Actually, this time series is not artificial. I pulled it out from the TRACE-21K simulation, which is completed, I think, by Feng He here in our department. It's a transient model simulation from last glacial maximum, 20,000 years ago to current day. I pulled one time series at a model grid point in North Atlantic. I think it's a surface temperature, yes. I plotted it here in depth order. So this is shallower depth, this is deeper depth. So you go from the seafloor down the core, and if you want to read it from time order, you have to read it from that part to this part. So so we have the age from the model output. This is 8,000 years ago, and here is 22,000 years ago. I assigned a segmentation rate, 15 centimeters per kilo, a random value, to give you some depth value. So I want to point out a few characteristics in this time series before I show you the convolution results. First, we have these wiggles, this decadal scale high frequency noise. Second, we have events of different time scale. This is oldest dryas cooling, which have a duration about 5,000, roughly 5,000 years. And then we have this boiling warming event, a spike here, around 14K ago. And then this aeroid warming around 13,000 years ago. And then this youngest dryas cooling here around 12. They're all of different time scales. And then I'm going to convolve the previous input climate signal with different impulse response function you have seen before. Still use g from 0.03 to g equals 4. 4 is here. And this g equals 100 is this pointy extreme case. So here's what you get. So the smallest g value, red curve, which corresponds to the weakest bell-turbation, and the biggest g value corresponds to the most intense bell-turbation. As you can see, when bell-turbation increases, the attenuation of the signal become more and more severe, and also the phase shifts become more and more severe. If you use this boiling warming event as a benchmark, there's some details about the attenuation. So first for younger dryas and volume warming, it's much more attenuated compared to the original input signal, like here to here. But if you look at this one, the aeroid warming event, it's not as attenuated compared to the input signal. So like these two events are subject to different attenuation compared to the relative to the input, although they have undergone the same observation. And for the older stress cooling, it's even weaker, only a tiny bit. So geologists spend most of their time trying to solve for the best chronology and trying to make their record as high resolution as possible. But the point that this figure can tell you, no matter how high resolution your record is, you still cannot tell the real story because it's simply damped. Like even if you have perfect mirroring, perfect measurements as high as possible temporal resolution, you are still not going to resolve this event because of the existence of observation. So a quick summary for forward modeling. We use observation as a linear filter. It can reduce the amplitude of the input signal and cause phase shift. This part is very easy and intuitive to understand. It's like passing through a smoothing filter. And given the same observation environment, events of different time scales are subject to different modification. So if you have a shorter time, if you have a shorter event, it will be subject to stronger attenuation. If you have a slower event, it will have a weaker attenuation relative to its input. And I have more quantification for different events and under different observation environments. It will be included in the supplemental materials. And it looked like a nice chart people can refer to for different combination of the situation. But in real world, no one knows what the black curve actually is. The only thing we have is this purple curve, is this bell-curved curve. This purple curve is taken from the previous slides when g equals 4. So in real world, what we are doing is we have this purple curve, the proxy record, but we're trying to make some inference about what the actual signal look like. We're trying to use this purple curve to infer the black curve. That's what we are doing in real world. So this give us some thought about maybe we should inverse the process. How do we back out this black curve if we are given this purple curve? Here we are going through this inverse engineering process. So how did we get the bell-curve signal previously? We use a convolution. We have an input signal fx. We convolve it with the impulse response function to get the hx. But right now our application is we have a proxy record here. It is bell-curved. We can estimate what the bell-observation environment is. So we kind of have this gx. We want to estimate this fx. How do we get this fx out? It's easy to do convolution in a time domain. If you want to reverse the procedure doing a deconvolution, it's kind of complicated, and sometimes you will encounter some matrix inversion problem, some singularity problem, which is kind of complicated. So what we are doing right now is we are utilizing the convolution theorem, which states that for linear time invariant causal filter, here's a causal. Remember we mentioned it previously. Given this type of application, a convolution time domain is equivalent to a multiplication in the frequency domain. So here, this capital H omega is a frequency response of our hx, and the frequency response is calculated by performing a Fourier transform, and similarly for f omega and g omega. So now, our convolution in the time domain can also be accomplished by doing a frequency multiplication in the frequency domain. Now the problem becomes easier, because remember we have hx, we have h, we have g. We want to solve for f. If we can conduct everything in frequency domain, we can very easily solve for this f, which is a recovery signal, which can reconstruct back the black curve. We get this f omega very easily. And then we can transform this f omega from the frequency domain back to time domain using an inverse Fourier transform. This basic function is provided in all the programming language, R, MATLAB, or Python. Okay, it seems very simple, it's very straightforward. But the problem is, for this convolution theorem to be valid, you have to satisfy three conditions. Linear, this is the most easy to satisfy, it's a very linear system. And then time invariant, which means our IRF, our impulse response function, have to remain the same through time, which again means the parameters we're using, Bell diffusion, mixed layer depth, and segmentation rate have to be constant through time. You will see this is not a very realistic assumption because it definitely will change through time, but this will be our first step. That's what we can do the best right now. And third is the tricky part, the causal filter. So this is a very common way of doing signal processing in electrical engineering. And most of their application is a causal filter, which means to get a certain point in the output time series, you only need the point that already happened. So you only need the information from the past. You don't need the information from the future. So in our case, remember, because perturbation makes things both upward and downward, so we are faced with a non-causal filter. I'm not going to go to the detail how do I transform this non-causal application to a causal application to apply this theorem. I'll show you the results next. If anyone is interested, we can talk about it later. I have to go fast. So, the purple curve and the black curve is the one before. The gray curve overlaid on the black curve is the recovered signal by deconvolving this purple curve using the impulse response function g equals 4. So we can see that this gray curve almost like get everything from the black curve. Even these high frequency noise, we have some little mismatch here. And we have mismatch here and here at the two ends. This is because we are using a taper when we're doing Fourier transform. So it will have some edge effects. The point here is if you want to apply this, you have to use a longer time series than the period of interest such that you can remove these edge effects. So far so good. Everything seems perfect. Like we can reconstruct back everything perfectly. But this is a very idealized case because we pretty much just reverse the process. We know what the signal has gone through and then we just inverse the process. That's why we can reconstruct back everything. But in reality, we're not that lucky. In reality, this blue curve here is the purple curve in the previous slide. I should have changed the color. Once the signal is mixed and preserved in the sediment, the geologists have to sample them to perform the chemical analysis and then to get us our proxy records. When they are sampling it, they don't sample it regularly. They sample it like irregularly. This red dot is a temporal resolution taken from real core data. I want to show you here is that in some of the records, they have very dense sampling, but in some of the records, it's not very dense. And sometimes we don't even know if the temporal sampling is enough to resolve everything. So also, when we are trying to apply deconvolution to a record like the red dots, we have to do interpolation because to make it time even, so we can perform analysis. So this might cause some issue because of the interpolation and the irregular temporal sampling. Also, in the previous case, we deconvolved the purple curve using the correct impulse response function. But in reality, we don't know what the actual perturbation environment is. We have to come up with some parameters to describe this system. This will left us with this incorrect parameter estimation issue. Third is when they're performing this chemical analysis to analyze the blue curve, there will be some measurement error, which is like the observation error in data simulation. Like any measurement will have some measurement error. So this will also cause some issue in our algorithm. So first we're going to test interpolation. So we mentioned the three. Interpolation parameter estimation and random noise. First, we're going to look at interpolation. This red curve is a temporary interpolated record from the previous red dotted curve here. Like we have temporarily interpolated them if it's a proxy record to make it tiny even. We get this red curve. And then we deconvolve it with the impulse response function, g equals 4, and we get this gray curve here. Compared to the gray curve we have seen before, this one, and then this one, you'll notice that this gray curve cannot resolve all these tiny, teeny details as a previous case. But it can recover all the other events perfectly, like this Bowling warming event from here to here, and this asteroid warming event, and then this dry cooling, and also this old dry cooling event is also well reconstructed. We just miss this decadal scale noise, which makes sense because when you are doing sampling here, you're missing something. You're missing information here and there in these gaps. So, but as long as it is frequent enough that you capture all the peak and values in the time series, we are still able to reconstruct all the real signal here. So for the interpolation, we can say that as long as the proxy record is not super sparse, we'll be able to reconstruct back the true input signal. This section, we're going to test the incorrect parameter estimation. So we're still going to use a red curve from the previous figure and use a gray curve from the previous figure. Red curve is our proxy record, interpolated proxy record, and the gray curve is a deconvolved record that uses a correct parameterization. And then we're going to test what will happen if we underestimate or overestimate each parameter. So for the first figure, we are going to keep the segmentation rate and the shape parameter correct. We're going to overestimate the mixing layer depth and underestimate the mixing layer depth, and compare the deconvolved value with the gray curve here. So when we assume the mixing layer to be 5 centimeters instead of 10 centimeters, we get this yellow-green curve here. So if you compare this thing to this gray curve, not only the amplitude is not fully recovered, the phase is also not fully recovered here. Which makes sense because if we assume mixing layer is 5 centimeters, we're basically saying this input signal hasn't gone through an intense perturbation because the mixing layer is only 5 centimeters. So we're not going to recover, we're not going to amplify this red curve that much to recover back the gray curve. So we end up with this yellow-green curve. But if we assume the mixing layer to be 15 centimeters, we recover a signal like something like this. It's much more amplified compared to the gray curve. Which again makes sense is if we thought this signal has gone through such a huge perturbation, we're going to stretch the red curve a lot to make it to overcorrect it to get and then we'll end up with this dark green curve. And for the remaining two figures, we go through the same procedure but with different parameters. This one we test on segmentation rate, and this one tests on G parameter. But the conclusion is the same. Is an overestimated perturbation, either by overestimate the mixing layer depth or underestimate the segmentation rate or overestimate the shape parameter. If you overestimate perturbation, you will get an overamplified recovered signal. If we underestimate the perturbation, we will get underamplified recovered signal. The point here is in real world, we can never give just one set of parameters and say this is the estimation we gave. This is the estimate we think this signal has gone through. In real world, every parameter estimation will have some uncertainty, and we cannot just get one recovered signal and say, hey, this is probably the true signal. A more educated way of doing this is we can try all the possible combinations. which is like a Monte Carlo approach by deconvolving this proxy record with various combinations, possible combinations of the parameters to get an ensemble of deconvolved signal. And this ensemble will provide us uncertainty bounds for where most likely the truth will lie. Okay, the third part, I'm going to test about noise amplification, which is when we are making these chemical measurements, we'll have some measurement error. So we try two cases, one is low noise level, one is high noise level. So the low noise level, you can barely see these yellow dots because I perturbed them very little. So it's almost overlapping with the red dots. And for the orange dots, you can see it's very, very noisy because we are using a crazy observation error. So here is what our noisy record looks like. So to perform deconvolution, first we interpolate them to make them time even, and then we deconvolve them use an impulse response function. We're left with these crazy amplified noise. We can barely tell what's going on. That's what has stopped people who have tried to attempt this approach because people say, hey, this is not real because you will be left with this noise. You cannot get anything out of this algorithm. But we want to show is that this can be suppressed. So if you turn on a filter called winner, which is like a mask you apply to the denominator in the frequency domain division, you will get something like this. This is much clearer compared to the previous figure. Remember our inverse engineering is a division process in frequency domain, which means if you have any close to zero values in the denominator, any noise in the numerator will be amplified. So we apply a mask to the denominator, replacing the zero values in the denominator to a close to zero but non-zero small values to suppress the noise. As you can see, it's much better. Although in this one there's still lots of noise, but we should do more work. We're going to apply another filter called Tanner filter. So Tanner filter is a filter that you provide the time series with the frequency cutoff value. So any variability that has a higher frequency than this cutoff value will be removed. So you will have to have some estimate roughly. You want to smooth the time series. You smooth out the random noise, the amplified noise, and then you are left with this gray curve here. As you can see in the low noise level case, it's much better, it's much clearer, and you can see all these events are very nicely constrained. But in the high noise level case, you still have these amplified noise, which makes sense because our algorithm doesn't know which variability in the time series is noise, which is actual signal. It doesn't know. It just take whatever you give it and then amplify it. So any wiggles embedded in the time series caused by the noise we have added before will be treated as a true signal, will be therefore amplified something like this, and we cannot remove them. So there's some caveats when you're interpreting the deconvolution results. First, make sure your observation error, like how big is it? If it's really big, you get something like this. You don't want to interpret them. Luckily, I heard that the Bendigo-Rayleigh measurement error is usually on this region, so we are here. But just make sure your observation proxy record, the measurement is accurate, precise, and have enough temporal resolution. Otherwise, you will be interpreting something that doesn't exist. So a quick summary for the inverse modeling. The entire procedure based on convolution theorem, but we have to do some innovation to transform our application to from a non-causal case to a causal case to make in order for the theorem to be valid. We test on three aspects: interpolation, which shows we have to have a high resolution record, otherwise we'll lose too much information. We also have an incorrect parameter estimation, which gave us an idea that we should always use a range of parameters instead of just pick one parameter. Third, noise amplification. We use two filters to suppress noise to make the filter stable. Emphasize again the importance of having a high quality proxy data, because if your proxy data is really bad, you cannot get much out of it. Next, I'm going to apply this method to a LR04 record in paleoclimatology. It's a collection of 57 sites, benthic O18 measurements. As you can see, some of them is very long, can go back to the 5 million years ago. Some of them is really short. And this is a very important data set in paleoclimatology. It's pretty much like the reanalysis in our community, like people use for various research. These 57 records are collected and orbitally tuned and also are put on the same age model to get a very standard set. And they also have a globally average, which is average across these 57, and you get this famous plot from current day to 5 million years ago. I'm not going to analyze the entire record. I'm focusing on one specific period here. It's about 130,000 years ago. It's called marine isotope stage 5E. This is a zoom-in plot of that time series from current day to 200 years ago. This is 5E we're concerned about. The reason why we picked this period is because this is the last major interglacial before Holocene. The CO2 is comparable to present day. And the temperature estimated at that time period is about 2 degrees Celsius warmer, and which makes this period a very unique case. It has been used frequently as an analog for the modern day climate, and people like to use it to make future projections about sea level and the global warming. That's why we picked this special period. There's some high-profile research trying to reconstruct and to give a reconstruction of the sea level estimation at that time. They estimate the sea level will be about 6 to 9 meters higher than present day. And what the method they're using is a probability estimate. And they use the LR04 data set, the one I just showed you before, as their prior knowledge of what's going on. And another research, for example, using the foraminifera oxygen O18 data to get a value for the sea level rise rate, which is 1.6 meters per century. These are all ocean sediment data, which potentially are subject to observation. That's why we want to take a look at this data set. So what we will do is we'll take this globally stacked LR04 data set, which will represent a global average value. We'll deconvolve this record and see how, and focus on this peak and see how it changes. Before we perform the deconvolution, we have to estimate our parameters: segmentation rate, mixing layer depth, and perturbation intensity. Usually from proxy record, you can get a nice time series of segmentation rate. In here, our segmentation rate is relatively constant. It's only from 4 to 5, like roughly from here. So it's relatively constant. And we can sample through the distribution of the segmentation rate to capture all the possibilities. For mixing layer depth, and perturbation intensity, these usually don't come with any proxy record. But there's limited research available that we can get a rough idea of what these values might be. So there's one research saying it's like around 10 meters plus minus 5 centimeters. And there's another research that is like around 5 centimeters plus minus 5 centimeters. And the well-accepted value in paleoclimatology is that it's about 10 centimeters. So in our case, we're going to try these three values, 5, 10, 15, to trying to provide a bound of this parameter. And for observation intensity D, it's also usually not available. But if you look at some old literature, you can get some rough ranges. And if you plug in these numbers into some classic segmentation rate and mixing your depth, you can see pretty much it will give you a G-value that covers potentially all the shape from 0.02 to 4. So later when we're performing experiments, we're sampling some segmentation rates from their distribution, and then we try these 3 scenarios of mixing their depth. And then for G, we just use a parameter that covers all the possible shapes, and to give us an ensemble of simulation of deconvolution results. Here's the results. I zoomed in the data into 100,000 years ago to 150,000 years ago. So 5E is this peak. These 3 plots shows 3 different assumptions about our mixing layer depth. And these colored, the black curve is a LRO4 global stack. And the colored curve is some extreme combinations of the V and G parameters. So you can see small G value in the distribution with two different G values. So we have extreme combinations. The same thing applied to these 2 plots. And as we can see that as mixing layer depth increases from 5 centimeters to 10 centimeters and to 15 centimeters, the variability, the recovered variability, keep increasing until here. When it's 5, it's roughly 0.2 per mil. When the mixing layer depth becomes 10 centimeters, it's roughly about 0.5 per mil. And when it becomes 15 centimeters, which is a very extreme case, we'll get our variability so amplified that it looks very, very sharp and noisy. And the magnitude here is around 1 per mil. If we composite all the possibilities, including the one you show on these 3 plots, we get this rebound that give you an uncertainty for the truth. And you get this uncertainty here for about roughly 1 per mil. We also applied it to a single record, UW-1117 in the LRO4 collection. The reason why we picked this record is that it has high sampling rate. There's lots of records in LRO4 that is very sparsely sampled, so it's not useful to use them to study for observation, because if you have a 5,000 years temporal sampling, the observation is probably, you cannot see anything because the observation won't cause that big phase shifts in 5,000 years. So this curve, the blue dotted curve shows the segmentation rates through time, and the red curve shows temporal resolution. And this is the record taken from this court. So we apply the same experiment setup and get these 3 plots. And notice that the curves in this figure is much simpler than the previous curve, because I smooth them with a much lower frequency cutoff radius. Because this is a single record, we will expect a single record to have higher noise. Since the previous is a globally stacked value, you will expect the noise kind of average out across the records. So this record have a higher noise amplification. So I use a stronger Tanner filter to constrain it, and then we are left with less spikes in this plot. And similarly, you can see when mixing layer depth increased from 5 centimeters to 10 centimeters to 15 centimeters, the variability gets progressively larger. So the summary for this application, we find roughly 1 per mil increase, 1 per mil not increase, change in the global stack in UW-1117 by applying deconvolution method. And for this single site, the noise amplification is more severe because there's definitely more noise in a single record than a globally averaged record. And considering The rough estimates used in geology is 0.1 per mil benthic O18 change is people use a 10 meters sea level change. And then 0.2 per mil to 0.25 per mil benthic O18 change to a 1 degree temperature change. We can see that the sea level estimates used based on the benthic O18 will be subject to change, potentially higher than the previously estimated value. Okay, that's the end of my defense. I really want to thank my advisor, Sean and Steve. I'm very lucky to have them to help me go through my hard transition during my PhD career. And I also would like to thank my committee members, Larissa Back, Michael Morgan, and Matt Hitchman, because the transition is really hard. I'm not saying something cliche, but without any of them, this PhD won't be possible. So thank you all for being on my committee. And I would like to thank my husband, Zach Hansen, who can't make it here. He's living right now in China. I feel very lucky to meet him in this program and have a lot of good memories here in the US. And thank to my family and friends for giving me emotional support in this long journey. Yeah, thank you for coming to my defense. If you have any questions, I would like to answer them.
Okay. So does anyone have any questions for Harmony? Go ahead, John.
Seems like magic. Did you feel that way too?
In the idealized case, yes.
Yeah.
In the real application, it's kind of tricky sometimes.
Yeah.
You have to make sure your record itself is good enough, because otherwise you will be interpreting something that doesn't exist.
Can you make arbitrary adjustments to your record, assuming that, let's take the noisy one that was on the left, the orange dots. Can you take like a series of 10 dots in a row and say, let's figure out what the average level of these is, and then let's take out half the distance that each of them is from that average and redo the whole analysis? Do you feel like that's unfair? And
You mean estimating the noise level?
yeah. If you artificially reduce the noise level arbitrarily, can you assess whether or not that was a reasonable thing to do with your method, or is it always just going to be a guess?
I have to refer to the literature using the error they provide.
Okay.
Yeah, so according to Steve, that the benthic O18 record is like 3%, like in the lower regime. So if you use a larger error, it's hard to tell. It's hard to say because you never know where the truth is. You have
Yeah,
to
I guess
believe
that's
what
right.
the people who perform experiments
Yeah.
tell you. Like they say our error is very small, so you will take the smaller values.
Mhm.
Yeah.
Okay, thanks.
Liz?
No,
Oh,
I'll
sorry.
save my questions. Sorry.
How does the estimate during the lasting regulation, how does that affect the signal estimates?
Oh, actually, if you want to get the exact value, like in this paper, you would have to deconvolve each record, remove these bias, and then perform their complicated probabilistic estimate to get back the values. Because I'm only performing on the pretty much the raw data, and to invert these benthic O18 data back to meters, you have to run some ice sheet model, like the physical model you use, and then perform some probabilistic estimate in this paper to get an exact value in meters. I didn't do it. It seems a lot of work. But my point is, like, if the raw data you are using as your prior have bias in it, it's definitely going to affect your posterior estimate from the used in the paper.
Anyone else?
I was a little bit surprised to see when you applied your filters at your high noise situation, you see that a very strong simplicity came out. Do you have any idea why that is the case? Is it inherent to the filters you use?
You mean this?
No, where you had a high noise situation, you used your two different filters.
Okay.
The 20%.
Yeah.
The artificial periods,
Here
yeah.
it comes.
Very good. The next one.
And one more, two more.
Oh,
Maybe stole the next.
One more.
keep going.
Right
There you
there.
are.
Yeah, there you see a signal, reconstructed signal with a very strong cyclicity on it.
Yes.
Why is that?
Because all the tiny wiggles in the orange dots is amplified. It looks very noisy. I want to remove them. So I use this Tanner filter in astrogram and apply this frequency cutoff radius. The theory behind this filter is also Fourier decomposition.
It
So
must be a cyclic.
yes,
cyclic
because
filter which you
because
apply.
for any arbitrary time series, you can represent it by a bunch of sinusoid waves.
Okay.
So the more components you have, the closer you can get to the signal you're trying to estimate. But if you set a frequency cutoff, you're removing lots of components away. So the left remaining components will become more and more sinusoidal, like very cyclic. Yeah, that's hard to. So it's hard to interpret these because from this pseudo proxy theorem, you know it don't exist, but you just apply to a real proxy data. You don't know where the black curve is. You might overinterpret this proxy.
Thank you.
Yeah.
Anyone else? Okay, maybe thank Harmony one more time.